Hello class, welcome to the next segment in lecture 23, and in this segment we're going to take a look at some of the things that we look for in the atmosphere to assess the potential risk for tornadoes on a potential severe weather day. So I'm going to be doing this by creating two different columns here, a list of favorable characteristics and a list of unfavorable characteristics. And for the most part, the list of unfavorable characteristics is just going to be the opposite of what you see in the favorable characteristics column. But in some cases that might not be the case, and for those particular criteria, we will discuss that in a little bit more depth. But the first thing that I'm going to show on the screen here is ideally you want a strong low-level jet. And by strong low-level jet, usually we look for at least a 30-knot wind at 850 millibars. And in the plains, ideally you want an 850 millibar wind speed that's due south or pretty close to due south. If you have a southwesterly wind at 850 millibars, that's not particularly favorable because you're going to be bringing in hot, dry air from the desert, and that also reinforces a feature called the cap, which is something we'll talk about a little bit later, and that's not something that you want to see if you want scattered to widespread thunderstorm development. If you got a southwesterly 850 millibar wind over the plains, that hot, dry air is going to make it harder for thunderstorms to go up, which usually is not something that you want, although you do want isolated thunderstorms, but you also, if you want a big tornado event, you don't want thunderstorms that are too isolated. So usually you want a due south wind in the plains, but in the southeast, what we refer to as Dixie Alley, that is Tennessee, the Carolinas, Florida, Georgia, Mississippi, Alabama, a southwesterly wind speed at 850 millibars, that actually can result in a tornado event. But ideally you want to do south wind at 850 millibars. And if you've got a weak flow field that is something less than 30 knots, usually you've got a flow field that's not going to be favorable for tornadoes. You can get tornadoes from flow fields as weak as 15 to 20 knots, but it's much harder to accomplish that. And again, the values that I put up here on the screen are not golden rule set in stone cutoff values. These are just values that appear to be favorable for the particular hazards that we're looking at. In fact, some of the higher end tornado events occur when you've got more intense winds at 850 millibars, so 40, 50, even 60 knot winds. And generally, the stronger the wind at 850 millibars, the more conducive the atmosphere is for tornadoes. And another thing that you ideally look for is steep near surface lapse rates. That is, as you go from the surface and go up, say, half a kilometer or a kilometer, you want the temperature to decrease very rapidly as you go up that distance. If it's if the lapse rates are very shallow, then that means your updrafts are not going to accelerate as much, and you're not going to have as much what we refer to as stretching. You want to take that, you want a nice robust updraft right from ground level to stretch out the spinning columns of air and increase the rotation. That's just applying the principle of conservation of angular momentum. If you say take something like a bungee cord, spin it around and then stretch it out, the process of stretching it out causes it to spin faster. So ideally you want that stretching to be enhanced, and the best way you get significant stretching is to get a strong updraft, and the best way to get a strong updraft in the lowest 1 kilometer is to have steep near surface lapse rates. And again, you can get tornadoes from shallower lapse rates near ground level, but ideally you want steeper lapse rates to get more robust stretching of the rotating updraft. And also you want supercells. Ideally, the strong to violent tornadoes are going to be coming from supercells. And as we talked about in the previous lecture, you want strong deep layer shear to get supercells to form. And typically you look for surface to 6 or surface to 8 kilometer bulk shear values of around 40 knots or higher. And typically more shear is better, but it is possible to have shear that's too intense. And if you have shear that's too strong, then you might end up tearing updrafts apart. So if you've got stronger shear, then you also want more buoyancy so that the updrafts have a better chance of maintaining themselves as opposed to a weaker updraft, which might end up getting torn apart. And a curious dynamic that comes in play in the southeast is you can actually have very intense shear and very little buoyancy, and somehow the updrafts remain intact, which is kind of interesting to see, especially considering usually strong shear tears updrafts apart, but in the southeast that doesn't seem to be as much of a concern for some strange reason. And if you got weaker vertical wind shear, that means you're less likely to get supercells and you're more likely to get multicells, which again can produce tornadoes, but they usually don't produce the strong, long-lived tornadoes that supercells do. And of course, if the vertical wind shear is too weak, then you end up with single-cell thunderstorms, in which case you can pretty much forget about tornadoes altogether if you've got single-cell storms. Another thing that you ideally look for is a strong change in wind speed in the lowest 1 kilometer, or wind direction in the lowest 1 kilometer. Ideally, you want, say, a south southeasterly wind going to a southerly wind at 1 kilometer above the ground. But again, the southeast, going from a southeasterly wind to a southwesterly wind also works. In fact, that works even better. But if you see that same pattern in the plains, a southeasterly wind going to a southwesterly wind, we talk about the same problem that we ran into up here, where a southwesterly wind around that altitude can actually limit the potential for thunderstorms to develop. And in some cases, it can outright eliminate any thunderstorms developing at all. And if you have a unidirectional wind profile, it's possible to get tornadoes from that, but it's much harder. So ideally, you want strong directional wind shear in the lowest 1 kilometer, which will really set those rotating updrafts in motion, and your thunderstorms will be more capable of producing tornadoes as a result. And ideally, you want isolated storm modes, which give you a better chance of supercells, which give you a better chance of strong to violent long-track tornadoes. You can get tornadoes from linear storm modes, but the worst thing that you could get is, say, something like a messy, disorganized storm modes. That is, the storms don't really resemble supercells at all. They're just kind of masses of thunderstorm that don't really have much organization to them. Those almost never produce tornadoes. But you can get tornadoes from, say, like an S-shaped hodograph. That is, if the storms go linear fast enough. But an isolated storm in an environment with an S-shaped hodograph, you can get a tornado from that, but it's going to be much harder to accomplish that because the storm is just not as organized as, say, a nice clockwise curvature that's present throughout the entire troposphere. And also, to get supercells, you want air that's really buoyant. So you want really strong instability to be present. Again, this is something that's kind of strange. In the southeast, you can actually get away with having a tornado event, a significant tornado event, in fact, without much instability. There's a lot of research going on in the southeast trying to determine why the rules seem to be different down there, why you can actually get higher end tornado events without much instability and lots of wind shear. Sometimes you'll hear that referred to as a low cape high shear setup in the southeast. But the southeast seems to, for some reason, play by its own set of rules than the plains does, and there's a lot of questions as to why that is the case, and a lot of those questions are still unanswered. And also, ideally, you want low cloud bases. So this is something that we kind of talked about in the previous lecture, how if your cloud bases are too high off the ground, then your thunderstorms, the air that comes out of the thunderstorms is going to be cooling very rapidly, and you don't want that cooler air infiltrating the updraft because that's just going to that's just going to inhibit the storm supply of warm, moist air, and that's also going to make it harder for tornadoes to form. You can get tornadoes in such an environment, but they typically are short-lived and not as intense. Usually, if you have to get a more intense tornado, you want a lower LCL, a lower lifted condensation level. And also, you want a nice, strong clockwise curvature in the hodograph. So again, we talked about that in the previous lecture, how if you have a strong clockwise curvature, that gives you a lot of streamwise vorticity, which means you're much more likely to get storms that rapidly become supercells, that become cyclonically rotating supercells, which have a better chance at producing tornadoes. You can also get tornadoes from straight hodographs, but it's not as, it's a bit hard. If you have to have a storm that's sufficiently isolated for a lot longer period of time. If a storm splits into a cyclonic and anticyclonic splits, those storms can occasionally produce tornadoes, and at times even intense tornadoes, but that process takes so much longer that the storm might not survive long enough to actually produce a tornado if that is the case. But also, veer-back veer profiles and barotropic atmosphere also not favorable for tornadoes at all. Well, they're not as well. I should rephrase that. I didn't mean to say at all. It's just they're much less favorable for tornadoes. So let's take a look at a case where we had a pretty high-end tornado event over North Alabama. This was the event that occurred March 19, 2018. And if you take a look at the sounding, we have pretty much all of the features that we had on the previous slide. The only thing that you can't diagnose from a sounding is the storm mode. If you want to diagnose isolated versus linear storm mode, you have to take a look at the synoptic skill setup, and we'll talk about that towards the end of the lecture. But if you look at the features on the sounding, you can see it has pretty much all the features that we talked about. The 850 millibar wind speed is 60 knots, and it's almost due south. The lapse rate's pretty steep. In fact, if you look at the actual parameter from the surface to 3 kilometers, it's about 7 degrees C per kilometer, but it's actually a bit steeper than that once you get below this little inversion, which is causing the value to be underreported. It's almost dry adiabatic in this in the lowest 1 to 2 kilometers, so those updrafts are going to accelerate much more rapidly in this environment. Deep layer shear. 86 knots. That's more than twice the threshold that we outlined in the illicit criteria that we gave. And instability, definitely a lot of it, 2,000 to 3,000 joules per kilogram of CAPE. That will definitely support supercell storm modes. And there is some pretty strong veering. The wind goes from due south to southwesterly in a pretty short amount of time. In about 1 to 2 kilometers, it goes from due south to southwesterly. So there is strong turning in the winds in the lowest 1 to 2 kilometers. And the LCL heights, if you can see the number here, between about 500 and 900 meters. So again, that's below the 1,000 meter threshold that we outlined in the criteria. And if you take a look at this photograph, this is just a monstrous clockwise curvature in the photograph. In fact, this will also usually a strong clockwise curvature in the photograph will show up in the SRH values. And here you can see the SRH values are 400 to 800. So there is a ton of directional wind shear present in this environment. And this was also a day where there were multiple significant tornadoes. I don't remember what the most intense tornado was. I think it was an EF3, but I believe it was also on this day where there was some massive hail in northern Alabama. This is kind of an unusual profile to see in the southeast. Typically, your severe weather setups in the southeast around this time of year in March are low Cape high shear setups, but this was more of a high Cape high shear setup, which was something that's of particular concern in a place like the southeast. But that's going to do it for this segment on a look of what sort of criteria we look for in the atmosphere to diagnose tornadoes. And in the next segment, we will do the same thing, but for damaging straight line winds. So with that, I will see you all in the next segment.